Hello, my name is Nikos Doukas. I am an associate professor in the Military Academy of Greece. And the present paper that I will present is on a method for protecting data being processed by the discrete Fourier transform on a remote computer system. Alexander, who is happy, thankfully been able to join, is the soul of this investigation. So he is also here with us. The problem faced here is enabling fast digital processing by using a discrete Fourier transform on microcontrollers that do not have very strong computational capabilities, such as those that we encounter in equipment for Internet of Things devices used for remote controlling processes and whatever else. So the idea is to use cloud or other external computer resources in order to pass some of the difficult calculations and more specifically the discrete Fourier transform in our case for faster implementation. And of course, problems arise immediately because the signals that will be transmitted to the external device for the calculation need to be protected against unauthorized access. And we will propose an encryption method based on a linear mixing of the samples of a signal group. The encryption will involve the time domain signal and the decryption the obtained signal spectrum. Of course, this could have been presented in the opposite direction, but it would be essentially the same. And there's also a security analysis that we will present for this. So, what is this useful for? We see that there is a deepening interaction between computer system and the physical world. So there exist increasing numbers of networks of portable microcontrollers that are physically embedded in real world objects. And the devices have more and more built-in wireless communication capabilities that allow them to connect via the internet and exchange data with many services, including powerful computer systems that exist and offer such kinds of services. There are two paradigms that are very popular at the moment: Internet of Things and smart things. Of course, one could think of other application paradigms where the same situation applies. So there are applications like surveillance, control, remote sensing, monitoring, image recognition, speech analysis, and other applications that require DSP. And in the core of many DSP algorithms, we have, of course, the Fourier transform, either usually in the discrete Fourier transform form or FFT for more efficient implementation. But in any way, it requires a large number of multiplications. It is still a heavy operation. And in principle, we'd like to have it in real time. So the use case says that we would like to exploit the widely available remote powerful computer systems for facilitating this calculation, passing the difficult job to someone else to do it for us and have the results back quicker. So the time domain signal data are uploaded to the remote system. The DFT is performed on the fast hardware, and the spectral components are downloaded. The signal data, as we said, must remain confidential, so it must be protected during the external transmission and processing. Essentially, we need to encrypt the signal, perform the remote processing, and decrypt the result. And enabling this, as we said, gives us the possibility to do better signal processing on devices that wouldn't be normally able to do that. So it advances the evolution of such systems. Now, going back to the first year electrical engineering, let's remember the Fourier transform. So it is a mathematical technique that transforms time, a time domain function, x of t, to a frequency domain function, x of omega. It is applicable to any periodic function with, if we call its period 2 times t, then it is represented as an infinite number, the sum of an infinite number of sinusoids. Frequencies form the sequence omega 2, omega 3, omega, etc. And the values of the amplitude and shifts of these are A1, A2, A3, and phi 1, phi 2, phi 3. Of course, not all signals are periodic. Usually, useful signals are not periodic. So, the technique applied for non-periodic finite duration functions is to transform them by assuming a periodic repetition. And even so, non-periodic finite duration is also a big discussion, but sometimes we can assume finite duration and then work from there on. Since we're in a digital world, the discrete Fourier transform is most often used, where the continuous signal has been sampled by a sequence of n sampled values, x0 through to xn minus 1, that are taken at regular sampling intervals, x0, 1, 2, etc., which are multiples of the sampling time delta t. The result of the discrete Fourier transform is an array that has n complex numbers which correspond to the amplitude and phase shifts of the sinusoids whose sum reproduce the signal x of t. So, the real and imaginary components of each frequency component are represented as R of m and I of m for the m component, y of m, and m, of course, has values 0 through to n minus 1 and are calculated by the relationships we see here. So it's a sum of, for the real part, it's a sum of the signal samples with the corresponding shifted frequency cosine. And similarly for the imaginary components, the sum of products is with the corresponding signs. If we observe here, the trigonometric components do not depend on the sample value, x 0 to x n minus 1. So they can be considered as constant numbers depending only on the values of the indices m and k. So we can construct these coefficients akm and bkm for index k as the formulas you see here, again with the cosine and the sine in each case. And the overall representation of the transform is simplified as we see it at the bottom of the slide. So it's a sum of xk, the signal samples, with their corresponding coefficient for the A for the real part and B for the imaginary part. In terms of complexity now, a DFT of length n has, in order to get a DFT of length n, we need n square floating point multiplication operations. These are the prevailing operations. Of course, we have side operations, but multiplication is considered the prevailing one. So, as I mentioned before, the fast Fourier transform was developed long time ago, where by exploiting the symmetry of the coefficients a and b, the multiplications are reduced to n log the base 2 of n, which is less than n squared, but still is a very big number. So the DFT remains a computationally intensive operation despite the fast Fourier transform, and remotely uh, available devices, which can include Fourier transform chips, so Fourier transform hardware, can do it significantly faster than any small microcontroller struggling to deal with everything else it has to do on the remote on the IoT device. Uh, as I said, for most practical applications, that we don't want these signals to travel in open air in a way that anyone can access them. So we need to prevent the possibility of non-authorized uh, agents accessing the data during the transfer and during the processing. The remote processing device not, can neither be considered as secure, so it's not secure, it's not trusted. It's just there to do the job, the dirty job. So it's outside the control of the organization to which the device collecting the signal belongs. This situation corresponds to the homomorphic encryption of samples of the real signal before performing the DNT on the remote computer system. So, homomorphic encryption is a class of encryption algorithms where we have invariants to remote processing procedures. Uh, the usual obstacle to using homomorphic encryption is the computational complexity. Homomorphic encryption algorithms uh, are best when they are specialized for one specific processing procedure because in this way they don't do more than is absolutely necessary for the processing to occur. In this case, we'd like a homomorphic encryption procedure that is suited to the DFT. What is most widely used is additive masking. The mask E must be formed in advance, and since we have n signal values, it will consist also of n values. A DFT needs to be performed on these, from which an array U of complex numbers will occur that contain the real and imaginary components of the spectral representation of the mask E. Encrypting, in order to encrypt the signal in the remote, in order to send the signal to the remote processing device, we need to first encrypting by adding on the corresponding mask. So the mask signal is then transmitted to the remote device, processed, and the DFT is performed on it. It's in a similar fashion as before, only that the result that we get contains is since the DFT is a linear operation, it also has added the spectrum of the mask. So the decryption corresponds to subtract the decryption of the result when we get it back, amounts to subtracting the corresponding components of the array U from all the result components that have come from the remote processing device. The cost, the cost of the for doing this encryption and decryption operation is the total time for performing these operations, and it is for a frame should be 3 times the number of samples times the time to do an addition on the device. What are the disadvantages of this approach? Uh, in order to do the masking, we need to perform the DFT over the mask. And so this again is a burden on the terminal microcontroller. We're aiming to unload, remove some of the computational load from the microcontroller, but now we have to add some back onto it. Also, the mask must be chosen depending on the value of the signal X. If this is not the case, then adjacent samples will differ by a significant amount and increase amplitudes of high-frequency components in the spectrum, and there's a risk of introducing distortion and not having a perfect reconstruction of the signal afterwards. So if we were to use a large number of masks, because essentially the mask is the key and we need to change the keys as usual, often in order to maintain security, we will require a significant amount of time to prepare all these masks. Of course, this could be performed in advance, but the amount of total time required to prepare many masks for many applications is something that makes this less attractive. Uh, so, especially with flow processing, when there are flows of data, as is the case with signal processing very often, it's this kind of masking is not that effective, and we would like to propose a better technique. The method proposed is based on the orthogonal transformation of the components of a group of process signals. So let's assume that there exists a signal frame flow that contains m frames. Each one of these frames will be represented by, of course, the signals that it contains. So we want to perform the DFT on all of these signals and obtain the corresponding spectral representation. So the random one of these will have a spectral representation that contains, of course, its complex, its real and imaginary parts as a complex number. So the proposed method provides the use of homomorphic encryption and decryption using orthogonal transformations over the matrix comprised of the signal frame samples x, uppercase x to uppercase x1 to uppercase xm. For this purpose, we need to choose an arbitrary binary orthogonal matrix D for the encryption. For the orthogonal matrix D, the matrix C, which will correspond to the decryption, is found by solving the system of equations shown in this table. And for any vector x of the signal vectors, the condition that will be satisfied is the one that says that we can recover the original signal by applying both transformations. So, for the example of m equal 4, a simple example, we can obtain this matrix for D, and then the corresponding C matrix will be this one. And once we have D, we can apply the transformation on the signals x1 through to xm. As a result, we get the encrypted signals now G1 through to Gm, and These contain sample values that are the result of the linear transformation. So they're not plain open text signals anymore. These can be transmitted then to the remote computer system, and the DFT will be performed on them at the remote computer system, and the resulting Q0 through to Q, the resulting components should be Qm minus 1 here, sorry, will be obtained on the way back. This again is complex numbers with real and imaginary components, and these have been computed according to the DFT as we analyzed earlier on. They are returned to the terminal microcontroller that can then use the matrix C in order to recover the true spectral components of the original signals of the X group that were sent over. And hence the M spectral component, M spectral representation of the signal frames Y0 through to Y-1 can be recovered from that correspond to the original signals X1 to Xm that we transmitted. In order to analyze the effectiveness of this solution, we can use two basic criteria: the increase in the speed of the DFT implementation in comparison with execution on the microcontroller, and the assessment of the level of data security uh, through the amount of resources required for the reconstruction on on a remote computer system that performs the DFT according to the initial data provided to it. The PROS method uses as the key the orthogonal linear transformation specified by the matrix D. So, in order to recover the encrypted signals X, the remote system should try from the G group of signals to recover X, so by determining D. The number of possible matrices that can be used for this scheme is determined by the equation that we see here. And to cut a long story short, for m equals 5, there are 83 times 10 to the 3 orthogonal matrices. For M6 is 28 times 10 to the 6, and for m equals 8, the value becomes 1.4 times 10 to the 14. So we see that it's very easy by increasing the size of the frames to increase the level of security. Already at m equals 8, the, the number of keys is significantly large. And depending on a message lifetime for a transmitted flow of signal, the lifetime may be shorter, so we can reduce the number of keys. For bigger frames, we can achieve better security. So in actual applications, we could have a certain number of pre-calculated orthogonal binary matrices and the corresponding inverse matrices C loaded onto the terminal microcontroller. They're not that difficult to compute. And every time, with a group of M signals, one of these matrices is randomly selected and becomes a different encryption key for each case. For measuring the increase in speed, we need to calculate the acceleration coefficient beta, which is the ratio between the time that the resources on the microcontroller would take to perform the operation. So we'll call that T0, and the time when required by the device to complete the process when performing the DFT on the remote device according to the proposed method, which is T. The execution time we have to consider to be n log to the base 2 of n. And so T0 would be given by m times n times log to the base 2 of Tm plus Ta, multiplication plus addition, in floating point, of course. And when using the proposed method, the terminal processor will only be required to do the encryption and decryption of m times n samples, which means that the encryption of one sample time is 0.5 times mu times m times ta, the time for an addition. So the value t is m squared times n times ta, and the overall acceleration is at the end log to the base 2 of n over m times tm over ta plus 1. So the essential factor determining the acceleration here is the ratio of the time required to perform multiplication to the time required to perform additions in floating point. And if we're talking about microcontrollers that do not support floating point operations at the hardware level, then an approximation to that would be the ratio between multiplication, time for a multiplication, time for an addition will be approximately equal to the bit length or the word length of the processor. For example, for a PIC32mm microcontroller, the acceleration would be between 30 and 100 times. So in conclusion, we have presented a method for data protection for securely transferring the DFT calculations to remote computer system in order to exploit their speed. And the method is based on the encryption of readings of a group of signals based on a linear mixing. The key was a binary orthogonal matrix. The number of possible keys can be chosen to eliminate according to the security requirements of the application. And decoding is performed by inverse linear mixing of the obtained components of the spectral representation of the signals. And as we said, this hopefully will enable the acceleration of DFT calculation by between 1 and 2 orders of magnitude, and hence enable more better DSP calculations on less powerful microcontrollers. So thank you for your attention. And if there are any questions.
Nikos, so thanks for interesting presentation. Colleagues, you're welcome to ask questions.
If I may, I'd like to ask Alexander if he would like to make the first comment as an honor to him and to express our happiness for having him here today. I don't know if he can hear us.
Alexander, do you hear? Okay, colleagues, you're welcome to ask questions.
Yes, I'm here. Sorry, I'm here. And I'm ready to answer all questions.
Okay, nice. Then let us pass to questions. Who would like to ask the first question?
Let me ask, please. Could we return to the page number 18?
Okay.
Here. And in the first part of the slide, we can see an equation, the equation, and I see that there is index L as well as upper limit that depends on L. Please, could you...
Correct, yes, it's 0. There is present a 0 because of the higher index must be m minus 1.
Okay, okay, thank you. Okay, thank you. And also another question. What is time complexity of the proposed method? Is it linear?
Yes, thank you for question. Thank you for the question. You can see that we use the binary coding and decoding matrix. So in real, we can say that for homomorphic encryption and decryption, we use on real the matrix multiplication. But in cases that we use only binary matrix, orthogonal matrix for encryption and homomorphic description, it's really we use only addition operation. Only addition operation. It's allowed to in the decrease the computational complexity. In comparing, for example, the universal homomorphic method in which used non-binary matters for coding and decoding. But we can say that for this special task, namely discrete Fourier transformation, we can use the binary matrix, which can decrease of using of such matrix allow us to decrease the computational complexity.
Okay, thank you. Thank you.
Other questions, please. If no questions, I will ask one question. Is your approach general, and I mean that it can be applied to other orthogonal transforms like discrete cosine transform, or it is suited only for discrete Fourier transform?
We decision the task for organized security Fourier transformation, but we use similar approach to decision another task of imagine processing on remote computer system. But I think that your question give us to follow to next research.
Thank you. Okay, some other questions. So, colleagues, it seems to me that we don't have question to the current presentation, and let me check one more time two presentations that have been absent. So, presentation number 188 by Bo Zhang, Jixu, and Jianchen Zhu from China. I do not see presenters. Maybe they will present next day when we have a reserve day for presentations. And one more presentation is number 2405 by Tomer Yeish and other scientists from Israel. Do we have them or no? I also do not see them. And as far as I know, Professor Harchenko has a written message to them, so maybe they will be at some special session. So we are coming to the end of today's schedule. And now I'd like to get some opinions, some recommendations, maybe some complaints Colleagues, you are welcome to say a few words concerning session, concerning the conference, and so on.
Thank you for reports and for interesting presentations. Actually, it was maybe if we have some space of time, maybe it's possible to really discuss some details that was not mentioned during the questions, and there is such possibility.
Thanks, Artyom. Please, colleagues, you're welcome to express your opinions. Maybe wishes to other participants. So, does somebody want to say something else? Okay, then I will say a few words. I think that we had good 4 reports today. Unfortunately, we didn't have 2 more reports, but anyway, we got new knowledge, maybe good new ideas, as Alexander said in his last presentation. And thank you for your participation. Thanks, Greek people, for organizing these conferences in Greece. As far as I know, it was the first time.
Well, welcome. It was a very great pleasure to help support this conference during the difficult time. And also, we have the pleasure of having some of the Ukrainian colleagues here in Greece, which is also very nice. And hopefully, next year it will be under better conditions.
Yes, I also hope that we will have the third conference 2 years later, and for sure we will have this conference in peaceful conditions, and hopefully we will see each other face to face, and I think this is the wish of all of us. So good luck, good health, and have new benefits, have new success in science, in life,